Okay, let's take a look at ELTE131 weak 10 sensor types. So here we're talking about input systems, components, or sensors is what we're talking about. Input system components / sensors. There's a lecture worksheet that you can get and you want to follow along. And you can watch this video by downloading the PowerPoint and then clicking the video, which you must have done if you're watching this video. Here's what you need to do for the quiz. Without reference, provide the definition and electrical terms for the proximity switches, limit switches, Hall effect, photoelectric, translucent, transparent, opaque, direct scan, photosensor. Explain in some terms the functional operation of capacitive, inductive, and Hall effect sensors. Describe the variants that determine sensing distance for capacitive, inductance, and Hall effect sensors. Give examples that are given in this video that relate the applications of sensors and limit switches to environmental factors, cycle time, fault sensing, and longevity. Explain in simple terms the operation of direct and reflective photosensors, and distinguish between appropriate applications for direct scan and retroflective scanning. So this lecture is and the videos are going to go over this, and we'll do the lab, and then you should be able to answer these. Let's start with a review of quiz 7. And so what we have for quiz 7 is right here, and explaining the difference between manual starter and manual contactor. The manual starter or motor starter has overloads. List the 3 types of overloads. Relays, this was from the last lecture. We have magnetic, similar to solenoid. Thermal, that's the melting alloy, the ratcheting, and then you reset it. And then the bimetallic, which was 2 dissimilar metals. So this was, I'm not going to elaborate on this because this was right out of the last lecture video. We went all the way through it. The motor is running and it's drawing more current in 15 amps versus 18 amps. It's going to trip in less time because the higher current, the more heat. Let's fix that. Define the following: full load current. This is the current that the motor should be drawing at the rated full load. So if you have a 1 horsepower motor, it's running at you're drawing 1 horsepower on it, that's the current that it should be drawing. Ambient temperature is the temperature that's surrounding the motor. It could be that it's just working in a cool or a warm environment, or that it's enclosed in a box. And put in a box, the temperature is going to go up. Service factor. The motor can exceed this nominal rating up here for the full load current for a short amount of time. Sometimes you just have a 1.0 motor where it really shouldn't exceed that full load current, but sometimes you have maybe like a 1.25 motor, whereas for a few minutes it could actually exceed that much current. You would set up and size your thermal overload accordingly. An enclosure would be the name of box that the motor controls are in. We then had to draw the following circuit, and you need to be memorizing how to do these. So the power circuit looks pretty standard there with the circuit breaker, the main contacts, the overload of the motor, and then it was jumpered here to bring us down from H2 to H3 from 4 to 1 in our fuses. So here's one way that we went over, and that was the jog make break. This is because what we're going to do is 2 push button control. So we had the start and we had the jog that would make break. So start just brings this one on, and we would get the motor contact here, and because this was closed, it would work. And let's say we wanted to jog. Well, when I push the jog down, my path would be on the lower rung, and this one would open, so therefore the motor contacts would never come in. That's a make break jog. The one that maybe you should have done would be this one right here. This one was right out of the lab. This might be the good one to memorize for the final exam. You're going to have to memorize the starter circuit, and then you're going to have to memorize how to hook this up. And finally, the other option would be to what we showed in class. And basically, we flatten this. Remember, this 1CR is on rung 2. So this was what we did in class, and you have notes on to basically, instead of having this vertical contact, we just kind of flatten the circuit here to get run in PB. So that was the last quiz, and D2L should have the answers to that quiz. Okay. let's go ahead to troubleshooting tips. And this is what the next week's quiz will be over. So when you're troubleshooting, probably the first step is to check for voltage on the load. If you have voltage on the load, well, you're in business. You just probably have a bad load, and that's a quick fix likely. If you don't have voltage on the load, maybe you should check for voltage at the source. If you don't have any voltage at the source, well, then maybe you've got blown circuit breaker fuses, something else. If you are going to then troubleshoot, it might be a good idea to turn off the power to the circuit. And once you determine that there's no voltage, you might want to turn off the power of the circuit, and you want to decouple the components for your best results. That's where I was pulling the fuses out. DMM, your digital multimeter voltage and continuity, can be used to solve a lot of problems, as the videos in the troubleshooting lab indicated. You don't necessarily need to check for continuity, or excuse me, current. You could use a resistance if you wanted to, but basically voltage and continuity is going to get you a long way. What is preventive maintenance? This is from your homework. It's so important in today's industrial plants. Well, you want to continually check your equipment and put it on a schedule so that you maintain it in top order, and therefore it prevents it from breaking. I guess kind of like your car. You change the oil every so often in your car so that you can expect it to run longer. You change your belts, you get transmission fluid. That's preventative maintenance, so that you don't have a large problem, fixing these small things so that you don't have a big problem. What effect does the power supply being unbalanced have on three-phase motor? So a three-phase motor, you can single phase a three-phase motor. What does that mean? Well, a three-phase motor has line 1, line 2, line 3. If you had that running and you pulled out, let's say, line 1, there's a chance that motor would keep running because it has direction, and it would run only off of line 2 and line 3. And if we only have 2 lines, that's called single phasing. That motor's not going to run very well, though, because it's supposed to have 3 phases. So you're supposed to have voltage between L1, L2, L1, L3, and L2, L3. But it's only got voltage between L2, L3. So what's going to happen? Well, it's going to run hot. And it's not going to run very well, and you could damage that motor. But that's what single phasing is. An unbalanced load would be if you had, let's say, 208 across one line, to line 2, 208 from line 2 to line 3, but if for some reason from line 1 to line 3 you only had, let's say, 150 volts, that's unbalanced, going to cause it to run hot and could damage it. First step in troubleshooting is probably check for voltage on the load. 2 things that can cause the coil to burn out, well, there's a few things. If it's too much voltage, if it's getting too low voltage, or if you are cycling it off and on rapidly or a lot, that could cause your coil to burn out. What problems can be caused by supplying voltage that is too low or too high to the coil terms to a contactor? So yeah, too high or too low. If you're too high, you might just cook that coil. If you're too low, it's going to get really hot and can damage it. Okay. And you can also, if you go too low, you can get it to chatter or to drop out. So those are some problems that can be caused. And if a magnetically operated device produces a humming sound, what are some of the potential causes? Well, if I'm getting a humming on this, it probably means that I might have too low a voltage on the coil. Okay, that's usually what humming means. Or I'm starting to get problems with a coil, that it's damaged. Okay, so what you probably have to do is check your voltage, be sure you're getting the right amount of voltage, and if you are, at that point, you might have to replace the item because maybe it's fatiguing. Okay, what parts of an electromechanic, and what you would do there is you could also check the resistance of that coil, against the manufacturer's recommendations or nameplate. What parts of an electromechanical relay can go bad? Well, the coil could go bad if you're giving it too much voltage or not enough, or you're cycling a lot. That could do it. And what you would do is you could have a problem with the resistance. You could check the manufacturing spec. You could take a look at it. Another part of the relay that could go bad would be the contacts. So the relay's got contacts that open and close, and what happens is if they're arcing a lot, they get pitted and then they fail. Okay, so that, and you would come, if it's a repairable contact, you could go in there and put in new contacts. How can you estimate the amount of work a motor is performing? Well, this was one that some people missed on the homework. The best way to do this is you could take a voltage reading on the motor, and you could use a clamp-on meter to get the amp rating of the motor. So what would that do? You could do VI, V times I, and that would give you the amount of power being consumed, and you do a little calculation there and compare it against the nameplate. So that's important you understand that. How does running a motor high or low, does the rate affect the motor? Well, if you're running it too high, it's probably going to be drawing more current. It's going to be it's going to get hotter. So you could burn out the coil, or you could damage that coil. Be sure that you understand these items here as explained in Demonstrate Lab, because that is what is going to be on the quiz. Review Lab 9. So I have a Lab 9B video. Okay. Also, in order to be able to pass the quiz, we're going to review the Lab B and the Lab 9A and B. Here's the video link right here. Go ahead and click these. They're pretty short, and I go through it, and just be sure that you understand. This will be on the quiz. You'll need to know how to troubleshoot. So here we go. What is a sensor / input? Okay, so we're talking about sensors, and what these are inputs to a system. It's a peripheral used to provide data and control signals to information processing or a control system. So the simplest would be, I guess, your computer, mouse, and a keyboard. That provides input to your computer. But what we might be doing here in industrial automation or controls, we might have a proximity switch that's wired into a programmable controller. Maybe another one that makes sense to you would be the door open and close switch on your car. There's a lot of other examples. Here's a quick minute and a half video showing you some of the items. Go ahead and pause the video and watch that. So what is the purpose of some of the inputs on machine? So to detect if a human worker could be harmed. So in automation, you're going to see something like this, and a good example might be a light curtain, that if you have to have your hands out of the machine for it to be operated, we will demonstrate what a light curtain is. To detect if a machine can be harmed, so we don't want the machine to damage itself. So for example, a robot has a force sensor on it. If the robot starts pushing too hard on something, the robot will know that, and it will pause. So it might be like a force sensor. To monitor production system operation. Well, this could be a lot of things. So, you might have proximity switches on the production system to be sure that parts are rolling down the chute like they're supposed to, or photo cells or whatever. So there's going to be a lot of different sensors to be sure that this production system is operating like it should. To monitor an individual work cell operation. So an individual work cell might be like a welding station. And so a welding station might have like a limit switch on there, so that when you put a piece of metal down, you know that the metal is there before you weld. Otherwise, you're just going to end up welding up your operation. So the limit switch will verify that you're actually welding on the item that you're supposed to. Okay. To determine the level of product quality. So you might have like a vision system or something on there that when parts go through, the vision system will take a picture of the part, and it will tell you automatically if it's a good part or a bad part. And to monitor status of production parts, something like that might be like a barcode scanner, so that when parts come through, a barcode gets scanned, and then you know how many parts you're making, and all the parts quality gets tied to that barcode scan. So these are some of the items that are available and related to what you just watched in that last video. Okay. In this class, we're going to talk about the three main sensor groups, and what these are contact. That means you have to physically touch them, and we've done some of this already. Non-contact, that's where you just have to be in the proximity of the sensor. and then process monitoring. We're not going to go into a process monitoring very much, even though we just talked about it in that last slide. Okay. Our main subgroups are going to be discrete, which is on and off, and analog, which is infinite states. Okay, so we have the four main categories then give us this: contact discrete, contact analog. Then we have non-contact sensors, which are discrete, and non-contact, which are analog. We are going to focus on discrete and contact sensors is what we've done so far. And this lab, this unit, is on discrete non-contact. So that's what this is. The sensors are going to be mostly discrete non-contact. That's what we're focusing on this week. We will focus on process monitoring in the PLC class. So even though I said that there was 3 sensor groups here, contact, non-contact, and process monitoring, we're looking at the contact discrete and non-contact discrete in this course. So let's start with discretes. Discrete has 2 conditions. It's on or off, high or low, 1, 0, true or false. That's how you describe it. So your light switch at your house, it's on or it's off. It only has 2 states. Okay, your weed whipper is either on or off. Okay, it's called binary or digital switching. If you hear discrete, binary, digital, that means all the same thing. It's either on or it's off. A good example that we've worked so far is a momentary push button. We've used a lot of push buttons in this class. You either push it and it's on or push it and it's off, or if it's normally closed, it'd be vice versa. That'd be momentary. If we wanted to maintain a discrete sensor, we'd have a toggle switch like your light switch. It's on or off. So that is what discrete digital sensors are. How will we use sensors in a control circuit? Well, we've mentioned all these items, but our control circuits are going to start looking like this. We're going to have a pressure switch in here, or a temperature switch, and we've already done the push button, that if the conditions are met on, let's say, the pressure switch, if it reaches 100 psi, it closes. So it's either opened or closed. It's digital. The temperature switch, if the temperature is met, it's either closed or open. Same as the push button, so you open or close. So this is going to be how discrete sensors, digital sensors, are going to look into a control circuit. Now, these sensors can be solid state, which means that they don't have any moving parts. They're electronic, or they can have moving parts. So these pressure switches here, for example, could be solid state, or it could actually have like a cylinder or diaphragm that moves in it to open or close. All right. Be sure you understand the difference between solid state and non-solid state. Analog sensors. Analog is different than discrete. It has an infinite range of conditions. Temperature could be 70 degrees or 70.3 degrees or 70.35, or it could be 75 or 83 degrees. That's an analog sensor. Another one that you might know is like your speedometer on your car when you're driving. It just depends on how fast you're driving. That sensor tells you some information. Analog sensors require some signal conditioning. Likely they're gonna do take some electronic signal and they're gonna process it and give you a value. Okay, typically they're solid state. There's going to be no moving parts, and they're going to require a transducer. Okay, so go ahead and take a minute here and watch my thermostat video to talk so that you can understand what we're talking about there. Okay, so you saw the thermostat. It's a mixture of analog, but it also has a discrete relay in there, a digital relay that switches. Okay, so combination. We talked a minute ago about a transducer. So a transducer converts one form of energy into another. In the sensors, we need to convert it into electrical so that the signal can be conditioned and give us a value. Transducers are solid state. Let's take a look at some scales. I got a picture of a scale here that could be like an old school spring scale. I hope you've seen it before. When you step onto this spring scale, it compresses a spring, and that spring has got a certain spring force or spring constant in it, and the scale goes up and tells you how much you weigh based on how far that spring is compressed. That is not a transducer, okay? That is a manual physical device that spins this knob here and tells you how much you weigh, versus a digital scale here is going to have a load cell in it, okay? And so when you step on this scale, the load cell converts force into electrical current, okay? Voltage and current. So you take that voltage and current and you put a computer in here, and the computer understands that that voltage and current means that in this case, I guess you weigh 129.3 pounds. So that's what a transducer, this one has a transducer, it's going to convert that force into another form of energy, electricity, okay? So we have our group 1 contact sensors. We've used some of these like a push button, for example, or limit switch. Physical contact is required. Limit switches and tactile means that you have to touch it, sensing. Limit switches are our most popular. Now, the lab or the quiz and stuff asks about the requirements for a contact sensor. Well, when you get a contact sensor, you need to know what size of a sensor you need. How are you going to mount it? What is the contacting device? What are the electrical properties of it? How much voltage and current can it handle? What is the operating speed of it? Okay. So what I've done here is I've come up with a little video here that you watch that explains some of those things. So go ahead and take a minute and watch this video. Okay, now that you watched that video, let's talk about the micro switch there. That micro switch on the robot, it was at the really little switch. It was discrete. It was that cam pushed it on or off. Okay, it's a contact sensor. That cam made contact with the little white plunger on there. This micro switch is inexpensive and very effective. And why did they pick it? Well, it was small, inexpensive. It had 2 wires on it, so it was probably just normally open switch. The robot just needed to know where it was. It was mounted with just a couple of simple screws, and the plunger was just basic, a linear on or off plunger. Okay, so those were some of the design considerations that they had to think about when they were mounting that on the robot. Non-contact sensors. This is what the lab is about this week. Okay, so this is the focus of the lab. And this requires presence rather than contact. You just need to be in the ballpark. Measure conditions without physically contacting them. Most common are your proximity, your photo optics, and your vision systems. We're not going to study vision systems in this one. We're going to study proximity and photo. So here's how it evolved. When I was a kid, we would go to the grocery store with my mom. In order to open up the door, you'd step on this big black pad that was in the doors. When you stepped on the black pad, the door automatically opened to the grocery store. Okay, that was a contact sensor. That was a mat that you stepped on. Well, they don't have those anymore. Now when you walk up to the door, there's some type of a sensor that senses your presence. Okay, just when you come up, a motion sensor. And when you get near the door opens up. Okay, that is a non-contact sensor. That's the difference between a contact and a non-contact. In your handouts this week, there's a very large PowerPoint on how all the solid state, or on how all these sensors work. So you are responsible to read that and go through it and understand it and see how it references this lecture. Okay, so what we have here is our solid state sensing technologies: magnetic read, Hall effect, ultrasonic, inductive, capacitive, photoelectric. You need to understand these. For example, ultrasonic uses would use some type of a sound or something like that, right? Photoelectric is going to use light. Magnetic operated relay is going to use a magnet. So take a look at these and be sure you fully understand that PowerPoint. Okay. Here's our sensing methods. Ultrasonic uses sound waves. Photoelectric uses light. Capacitive, electrostatic, inductive, electromagnetic. Okay. So this is in that book. We're going to break it down here in a minute, but ultimately you're going to need to understand this. The first switch that we're going to look at is called a reed switch. So a reed switch here has contacts that move and it has due to magnetism. And this is not a solid-state transducer. It is not a solid-state transducer. The Hall effect sensor that works on magnetism is. So go ahead and take a minute and watch the reed switch video and be sure you understand how that works. Proximity switches. These are solid-state devices that detect something that comes within a range. The range is variable. An inductive proc senses metal. A capacitive senses things that have a dielectric constant of greater than 1.2. Okay. How does the inductive procs work? It is discrete. The inductive procs, even though it's solid state, is either on or off. Okay. It's non-contact, and it uses an inductive field to sense metal. So you think, here's a coil of wire with current through it, and you get this magnetic field. And so it's similar to what we talked about with our mutual inductance for a transformer. If you have a magnetic field and you put a piece of metal in around it, you're going to get induced eddy currents in the field due to mutual inductance. That is going to affect the strength of this field. The sensor understands that the field is being affected, that means there's some metal in the way, and then it trips, saying that, hey, I've got metal in the way, okay? So it works on that magnetic field, that inductive field, to sense metal. Like I said, similar to what we did with a transformer. A capacitive prox is also discrete. It's on or off. It's solid state. It's non-contact. This uses an electrostatic field to sense charged particles. So in this case, there's an electrostatic or electric field here. When you put an item, metallic or non-metallic, into this field, it's going to affect the field. The field is not, it's going to be interrupted a little bit or modified, okay? And when you get your waveform to change, then the sensor knows that there's something there, okay? So the capacitive works on that electrostatic field. We're going to take a look at these here where inductive is doing metal. Capacitive is ideal for sensing fluid level and powder granular. Okay, so take a look at the proximity video here and understand the difference between inductive and capacitive. Okay, photoelectric switches. Photoelectric switches sense when light is reflected. Okay, they're solid state. They're going to be off or on, and there's three main types. The three types of photo switches are separate, where you have an emitted collector on each end, a retroreflective, where you need a mirror, and a diffuse that uses the natural reflective properties of light. These are slides out of your notebook. So here's through a beam. This is separate. The emitter's on one side, the collector's on the other. So you shoot light across here. If for some reason you break the light, then this is no longer receiving the light, and therefore the sensor knows that there's something in the way. Okay, and that's what we saw, what we're going to see in a video. Okay, here's take a look at what it's suitable for. You see this on light curtains a lot. Retroreflective scanning. There's a mirror. So instead of having the emitter on one side and the collector on the other, they're contained in the same unit. Okay, and therefore you need a reflector. Or you could use, if the item that you were trying to figure out was very shiny, maybe you were manufacturing something that's very shiny, well then this would automatically read it, okay? So take a look at the pros and cons of this and understand retroreflective. Then the other one is diffuse. So the emitter and collector are in the same sensor, but what is bouncing off the light? The target is not a mirror. It just depends on the color of the target, knowing that white light reflects a lot, so this is likely to reflect a lot of light if it's white, and then it would know that something's there. Or if it was black, well then it wouldn't reflect the light, okay? And so if you put something that was white then in the middle, it would reflect it. And the video is going to show you how that works, okay? So you want to take a look at the benefits of a diffuse proximity sensor. Where's that video? It's right here. So you're going to pause right here and watch the video. Pay attention to how these photo switches are working. So the scanning methods, this is a little more in depth than the three. You want to take a look at these about specular, polarized, okay, and convergent beam. These talk about how you might use a different scanning method. For example, if you have something that's really small, you could use a convergent beam or something at a very fixed point to do something that is very, very small, okay, whereas a limit switch wouldn't work, okay? But you want to go through and take a look, and this is right out of your notebook, it's in there, and see which one of these works for different situations. For example, here's polarized light. When, let's say, light moves through space, it moves in all different directions. We know that light is a sine wave. It goes up and down, almost like electricity. It's a wave, but it's going in all different directions. It's not any particular direction. When you look out the window, same thing. You're seeing light traveling randomly all over the place. Well, when you put a filter in here, this is almost like a fence, okay? So if you had all these sine waves coming through here, going in all different directions, once it hits this fence, it only lets the light come through in one direction, okay? So this is what polarized light is. Let me give you some examples. If you were in a subdivision where they're putting in a lot of houses right next to each other, what they're going to do is they're going to put windows on the side of the house, and they're going to be polarized up and down. The neighbor's house, the windows are going to be polarized left and right, okay? And so what happens is when you look out your window, the vision out of your eye is polarized vertically, okay? So that when you look in your neighbor's house, whose window is polarized horizontally, you cannot look into their house because the light is polarized, and there's a filter between the two windows. How about sunglasses? You heard of polarized sunglasses. Well, the road, when light bounces on the road, it has a tendency to flatten the light because the road is horizontal, okay? So instead of polarizing the light, up and down, it would polarize the light left and right horizontally until you are trying to avoid glare and everything like that. You put your sunglasses on. Well, if your sunglasses are polarized opposite to the glare, well, then you won't see the glare. You'll still be able to see fine. You just won't see all the horizontal light or the glare off the road. So manufacturing, if we have something that's shiny, like a can or something on top of a can that somehow flattens the light, well, that might be a good application for polarized, and then we would be able to sense the objects there. Let's take a look at a light curtain. So this is a machine, and this red here indicates there's light going between the emitter and the collector. It's discrete. It's going to be, you're either going to sense yes or no, on or off. It's non-contact. This is a separate photoelectric. So it's a through beam, separate. Emitter on one side, collector on the other. If you put your hands in there, it's going to trip. Here's a very quick video showing you how a light curtain works. So there's other non-contact discrete sensors that we talked about. There's ultrasonic, magnetic Hall effect sensors, infrared sensors, and these are all solid-state transducers, okay, similar to the proximities in the photo that we talked about. So these are in your handout, so you want to take a look and just understand. You've probably seen these around. You might have them at your house. Maybe you've got lights, that motion detect lights at your house that come on at night, or maybe you've got something on your front porch, a camera that comes on when somebody comes to the front porch. There's different types of other non-discrete proximity sensors. The final group is group 3 process monitoring. I'm just going to mention it. We're not really going to go over it. This measures the status of the process. It could be contact or non-contact. So for example, the RPM of something. So you could use a magnet, or you could use like a probe, something that you would put on a device that every time the magnet came spinning by a certain point, it would register or a probe. You can just sometimes, I think you did that in 109 where you put, I think we do that later on, where you put the RPM meter on the motor and you just see how fast the motor's spinning. So RPM is a process. It's going to be analog. Temperature, pressure, vision. So you might want to know exactly what a temperature is, exactly what a pressure is, if it's 76 degrees or if it's 76 psi. Vision system, good or bad. These are items, typically analog, feedback, that are used in more complicated applications. We're not necessarily doing process monitoring here, we're just talking about them. Here's an example, a turbine meter. Measures flow. So you have a turbine meter here. If you push a bunch of water through here, this turbine spins. Okay. Contact, yeah, the water is making contact with the meter. Okay, so it's spinning. It's going to return an analog, because it might be 6 gallons per minute or 7.3 gallons per minute or whatever. But when this turbine spins, it sends an electrical signal, and we're going to have to process that signal with a computer to see what happens. Okay. So with that said, you're finished. Turn in the completed lecture worksheet here, and you'll receive credit, and then you'll get the next assignment.